So we did cover now two examples. The first one was simply one-dimension conduction problem, and we applied Dirichlet boundary condition, 100 degrees C in here and 20 degrees C in here, and we used backward finite difference method and central finite difference method to get the temperature distribution. This was case number one. In case number two, we did change the boundary condition to the right side to expose the surface to a fluid with T infinity and H, and we kept Dirichlet boundary condition on the left side, also to get the temperature distribution at all nodes, and then we got extra node on the boundary here. Then we show that we still can apply the finite difference method for the interior nodes, and when it came to that outside node here, we did apply the energy balance method to be able to get an extra equation for that surface node. I would like to take the example to a little bit of higher level. So I'll take example case number two, but what I'm gonna do, I'm gonna add a heat generation to that one-dimension bar. These examples is just to practice how to deal with a problem in the simplest level, but with different boundary conditions. So when we went from Dirichlet boundary condition, mixed boundary condition, I will go with mixed boundary condition, but I will add heat generation to it. And then I will go for last case, it's gonna be a little bit mixed, which we have one phase exposed to convection, heat generation exist, but we will isolate one of the phases. And these are the very common cases that we're gonna apply solution for when we deal with the finite volume method. So I'm just going through this example here using the finite difference method, but we will repeat the same condition, but going into two-dimension problems more using finite volume method. So it's good practice to do that with these simple examples here. So in the next example, what I'm planning to do is I'm gonna call that case number three. I will have a bar. This face is kept at 100 degrees C. This face is exposed to a fluid. T infinity is equal 20. H is equal 10 watt per meter square Kelvin. Thermal conductivity of the bar is 10 watt per meter Kelvin. The length still 0.6. And the additional information here that this bar has a volumetric heat generation of 10 to the 4th watt per meter cube. And what is required is to get me the temperature distribution using finite difference method. By now, you should be, guys, aware that the finite difference method, if you use backward or forward, finite difference method, the error is of order h. The central finite difference method has an error of order h squared. So if you pick your h 0.1 meter, like what we usually do with the other cases, your error will be in the first digit within 0.1. But if the h is 0.1 and you are using the central finite difference method, the error will be in an order of 0.01. It's h squared, which means that you are getting better information. Again, the error is not noticeable here using different finite difference method, but because it's a very simple problem, but that's a scientific quantified error for each one of the methods. So what I'm gonna do here, I would like to get the temperature distribution for this case. So that's my design. That's step number one. Number two, what's my model? So that's a design. Again, I'm going through the systematic steps. What's my model? My model is the Laplace equation, partial 2t by partial x squared. But in this case, I cannot ignore the heat generation term. So that's actually k dot over k equals 0. Steady state, heat generation sources exist, and this is a second derivative. So that's actually the constant thermophysical property as well. So this is my governing equation here. So this is the equation that I'm planning to discretize. If you solve analytically, you have to integrate and so on, but now I'm gonna discretize. So I'm gonna use step number three, I'm gonna use the central finite difference method to discretize this equation. So let's draw that in a large scale a little bit. That's 100 degrees C. I'm going to divide my domain into 0.1 element. So that's node 5. I will keep it the same order: 4, 3, 2, 1, and node 0. And this surface is exposed to T infinity and H, and we have the value for that. And remember that that bar contains Q dot. And that Q dot is everywhere, okay? Okay, so let's see how we're gonna deal with that problem. Again, I'm gonna use central finite difference method. I'm just gonna need the second derivative. So partial 2t by partial x squared at any node I is expressed by ti plus 1 minus 2 ti plus ti minus 1 divided by delta x squared. And this is my delta x distance, and delta x is the same for each node. So let's apply that for this equation. So if I want to go for node 5, the governing equation will be now if you put this into this equation, let's simplify the equation first. So ti plus 1 minus 2 ti plus ti minus 1 divided by delta x squared. I'm going to multiply both sides by the two terms by delta x squared. So this will be q dot delta x squared over k equals 0. So that just simplify the equation. So you can apply this equation quickly and repeatably in a repeatable way for each node. So for node number 5, I need the temperature to the right of the node I. This is my node I now. I need the one to the right minus 2 of the node of interest and the base node plus the temperature before plus that term here. So let's calculate that term, q dot delta x squared. Remember, this is a constant added value all the time. Q dot is 10 to the 4th. Delta x is given by 0.1 square divided by k is 10. This will be 0.01. This will give me 100 over 10. So the value is 10. So as if I'm having a constant added value of 10 in each equation. So if I go for node number 5, the equation will be T4 minus 2 T5 plus 100 plus 10 equal 0. For node number 4, it's going to be T3 minus 2 T4 plus T5 plus 10 equal 0. For node number 3, it's going to be T2 minus 2 T3 plus T4 plus 10 equals 0. For node number 2, it's going to be T1 minus 2 T2 plus T3 plus 10 equal 0. For node number 1, it's going to be T node minus 2 T1 plus T2 plus 10 equal 0. Now we come to node number 0. I could apply the energy balance method. Let's do that first here. That's something easy to do. So I'm going to magnify or scale up that node here. This is node number 0. I'm having T infinity and the H in here. Okay, and this is node number 1. So step number 1, you have to draw the control element, which is a square of a dimension delta x surrounding the base node, which is node number 0. So because I'm doing one dimension problem here, I'm going to draw the left side of that control volume or control element. Then the one on the right is going to be on the space, so I'm not going to include that. Then step number 2 or condition number 2, you assume all the energy are coming in. So there is energy going into that element. I'm going to call that Q1. There is energy going into this element. I'm going to call Q2. And remember, this element has Q dot inside. This distance here is delta x over 2. Remember, this is delta x. This is delta x over 2. So let's write down the energy balance equation. Energy in, so I'm going into node 0. energy in plus energy generated equal to energy out plus energy stored. This is 0 for steady state condition. This is 0 because all the assumption, all the energy are assumed to be coming in. Now, E generated is not 0 now because I have a Q dot. So E generated is calculated from Q dot times the volume of the control element. So this will equal to Q dot. What is the volume of the control element? I need the volume of this element, which is delta X over 2 time whatever that height times the depth. As we mentioned before, the depth is always assume 1, and whatever the height is, right? It's assumed to be one-dimensional problem, and you will find that the area will be totally canceled out. So I can write down this as like area, which is into the page times the thickness, which is delta X over 2, and keep it that way. So this is the surface area times the thickness that give me the volume of the element here. Okay. Now let's go into the E inlet. We have actually two sources of energy coming into that control element, right? So I have Q1 that's coming by conduction. So it's going to be K times A times T1 minus T node over the distance between the selected nodes, which is delta X. I have also Q2, that's convection, which is H times A times T infinity minus T node. Again, energy has to be assumed coming in. Now, I will substitute into the energy balance equation. So it's K A T1 minus T node. I can divide that by delta X plus H A T infinity minus T node plus Q dot A delta X over 2 equals 0. A will cancel out. Multiply the equation by delta X over K. So I'm going to have T1 minus T node plus H delta X over K. I'm going to distribute that term over the two values between the parentheses. So this will be T infinity minus, again, H delta X over K times T node plus, I'm multiplying by delta X over K. So this will be Q dot delta X squared over 2K equals 0. Now, this will be T1 minus T node plus H delta X over K. H is 20, delta X is 0.1, and K is 10. So this will give me 0.2. So that term here is 0.2. So 0.2 times T infinity, which is, let me double check the values. H is 10 actually. H is 10. So I'm going to get 0.1. That's 0.1. T infinity is the 20 as a value. Okay. Minus, again, H delta X over K is 0.1 times T node plus, let's calculate that term here, Q dot delta X squared over 2K. Q dot is 10 to the 4th, 0.1 squared over 2, and K is 10. So this is 0.01 times 10 to the 4th. That will give me 100. Cancel with the 10 is going to be 10 over 2 is going to be 5. So this will be 5 equal to 0. So what we have here, we have T1 minus, this is T node minus 0.1 T node, so it's 1.1 T node. Okay, this will give me 2, right? Plus 5, so this will give me 7 equal to 0. And this is the equation for node 1. If you go back for the previous equation that we got when the heat generation was not exist, just for a comparison here. I think, yeah, that's a problem here. So you'll find that node 5, it's the value 100 increased by the heat generation term. Node 4 also increased by the heat generation term. Node 3 increased by the heat generation term. Node 2 increased by the heat generation term. Node 1 increased by the heat generation term, which is Q dot delta X squared over K, right? And when you go for node number 0, this was the equation without the heat generation. And now this value 2 increased by 5, right? And this 5 is the value of the heat generation in half volume or control element, right? Because each one of these applies for a full control element, but this is only applied for half control element because it's the small element in here. So this is just a confirmation that numbers make sense right now. So what you're going to do now is to construct your matrix. So I have T node, T1, T2, T3, T4, T5, and I would like to, just to make myself a little bit arranged here, and I don't mess up the alignment between the numbers. Okay, just a little bit of organization here. So let's take node number 1 equation. So I have 1.1 minus, then I have 1, I have 0, 0, 0, that's T node, T1, T2, T3. Oh, I still have more. T node, T1, T2, T3. Oh, I'm still missing actually more than that. So, okay, let's give it space a little bit. So that's 1, 0, 0, T1, T2, T3, T4, T5 is also 0, and the free term is -7, right? So let me just make my network to arrange the number in a better way. Okay, as much as I can here. Okay, let's go for node number 2. Actually, node number 1, we finished node 0. That's node 0, actually. Oh, I think, okay, that's node 0, actually, guys. Okay, now going for node number 1, which is this equation here. I have 1 in T node. I have -2 for T1. I have 1 for T2. 3, 4, and 5 are 0, and the free term is -10. Go for node number 2. T1, T node is 0, T1 is 1, -2, 1, 0, 0, and the free term is -10. Next equation, node 3, 0T0, 0T1, 1T2, -2, 1, 0. Okay, 2, 4, 6 values, 2, 4, 6 values, and this is also -10. I will have 0, 0, 0, 1, -2, 1. That's node 0, 1, 2, 3, 4. That's node number 4. Now for node number 5, I will have, that's -10 as well. For node number 5, I have 0T node, 0T1, 0T2, 0T3, 1T4, -2 for T5. The free term is 110. It's 110. Okay, now I have my matrix constructed. You solve that by either the MATLAB, or you can use the iterative method. And I uploaded in the second week, I uploaded you an Excel sheet for both Jacobi and Gauss Seidel or Seidel iteration method. So you can use any one of them. The MATLAB code actually will be loaded this week. I have a MATLAB code that's only, I don't recall if it's actually for heat generation or not, but I wrote a MATLAB code to help you solve one-dimension problem. You can take it as a fundamental case, then you can actually change as needed. So with this, I can solve and get T node 182.5. I got T1 193.75. T2 is equal to 195. T3 is equal to 186.25. T4 is equal 167.5. And T5 is equal 138.75. So if I draw that temperature distribution here, I should see the following here. This is 100. 1, 5, 4, 3, 2, 1, and 0. And here I have T infinity equal 20. So I got 182.5. I got 193.75. I got 195. I got 186. And I got 167.5. I got 138.75. And I got this. So it sounds like I'm having a kind of increase in temperature, then it goes down after that, like this. If you guys recall the analytical solution for this equation, if you do the analytical solution, you will end up having T of x, it's equal minus Q dot over 2kx squared plus C1x plus C2. So the temperature distribution when you have Q dot is no longer linear, like this case here, when you don't have a heat source, but when you have a heat source that comes in a parabola shape. So that's why the temperature distribution looks like in a parabolic distribution here. If I compare that to the case when the heat generation was not exist, I'm just recalling the value of the temperatures. Let me see the values. I think that's goes in here. I'm just recapping the values here. So the values was actually, this was 100, this was 95, this was 90, 85, 75, no, actually 80 first, 75, then I got 70, then the 20 here. So this was a linear distribution before you have the heat source, but now we have the parabola distribution here. And the increase in the temperature values here, it's becoming because of the heat generation source that exists in that problem. So this is how we utilize the finite difference method and the energy balance method to solve a problem exposed to when there's Dirichlet boundary condition, then a Newman boundary condition or a mixed boundary condition for both of them, but also include a heat generation term or a heat source term into the problem.